Great. So happy to be here. My talk today is called From Being the Graph to Feeling Magnetic Fields, Designing and Theorizing Learning for Diverse Ways of Sensing and Moving. And as I mentioned, I'm Sofia Tancredi, and here from the Wisconsin Center for Education Research at University of Wisconsin-Madison. So I want to start us off by introducing you to a student I met a few years ago. Let's call him Connor. So Connor came into the after-school learning centers where I worked, and he needed help with his math homework. So we invited him to show us what it looks like right now. So he got out his problems and started on the first problem. He started getting a little lost in the numbers, and as he was working through it, his head started drooping a little bit. And then he got to the second problem, his body started kind of collapsing onto the desk. And by the time Connor reached the third problem on his math homework, he was laying flat on the floor of our learning center. So it does. So what's going on here? What about the cognitive activity of doing math is making his physical body so tired? Then later, Connor stepped up on a rockable balance board we had in the learning center. And standing on that balance board, he had a kind of new energy in his body. And he was able to work through 10 problems from his math homework while rocking on this balance board before feeling like he needed a break. So what's happening there? Kind of traditional theories around cognitive load would suggest that adding a task of trying to keep your body balanced on this board should make it more difficult for you to work on a math problem, yet that's not what we're seeing. So these questions highlight this central issue in my research, which is the relationship between the body and learning. It's been recently recognized in the cognitive and learning sciences that the body and our interactions with the environment play a really critical role in giving rise to cognition. In the current climate of technological advancements, it's especially important to think about the uniquely human aspects of intelligence, and grounding in sensory-motor activity is one critical aspect of that. And at the same time, emerging technologies open up so many more possibilities for the kinds of ways we can interact with our bodies, which can give rise to new forms of learning. There's some examples of those that you'll see. So in my research, I'm interested in tuning this fit between the body and education. So I use design-based research in the kind of learning sciences tradition, meaning it's very theory-driven, taking theory, using that to kind of crystallize, well, according to theory, this should work, and then seeing, does it work? And then based on what we learned from that, both revising the theory and the design iteratively. And in my work, I usually start in a very learner-centered way, kind of centering the bodily experiences of learners who experience friction in typical class environments, and thinking about how we could redesign that, and then building towards what it would look like to apply things in actual learning ecologies like schools or museums. In each project, I seek to reimagine a norm of bodily engagement in education. And to do that, I focus on the marginalized, on learners who are currently marginalized, and the embodied resources that they bring. So things that they are good at doing with their bodies, and how we could kind of take those up to position those as resources for learning. And through the, sorry, before I tell you through that, wanted to highlight that 1 in 6 kids receive special education services. So in my work, I take those 1 in 6 kids as kind of helping us understand where our default norms are falling short, and where we can rethink the way that default instruction works for everybody. So the work that I do with those kids is part of building tools that are intended for use in inclusive settings for kids in special ed and kids in general education, and kind of freeing up, bringing in the body in a different way for everyone, and recognizing the diversity that's present in all humans. Okay, so because of centering these embodied resources, this brings me to focus a lot on sensory and motor modalities that don't tend to get a lot of attention in education, things like the bodily sense of balance or tactility as resources for exploring concepts. Drawing on these, each project seeks to foster conceptual learning in a STEM domain. I've mostly worked in mathematics, but a little bit in other science areas. And across that, each project brings in co-designers, so researchers in different disciplines, people with relevant lived experience, in order to kind of, and practitioners in order to bring in all the stakeholders that can kind of inform building something that could actually work in a real learning ecology. So today I'll share designs and data from 2 design-based research projects. We'll spend a little bit more time on this one than that one probably. The first one's called Balanced Board Math. Second one is called TeleTangibles. And then we'll open on to a broader vision for where I see this work going. So let's start with Balanced Board Math. This is a balance board. You might have seen them. They're used in occupational therapy. They're also used as a productivity tool. So you might have seen them in many contexts. So the norm that this project focuses on is the norm of limiting bodily movement. And in classrooms, kids are typically asked to sit pretty still and not engage in things like fidgeting. So this project takes inspiration from stimming. Stimming is, fidgeting is could be conceptualized as a form of stimming. Stimming is kind of repetitive motor activity. It was first characterized amongst neurodivergent people, but it's present amongst everyone. It's just that neurodivergent people's stims have the most friction with expectations in classrooms. So this project centers stimming as a resource for learning. And in particular, it focuses on stimming. A common form of stimming is bodily rocking. That engages this bodily sense of balance, the vestibular sense. So that's kind of a core thing that this project is exploring. And the design we'll talk about today is called balance graphing. So the Balanced Board Math project has looked at many different concepts, but the specific activity we'll look at is for functions and graphing learning. And this was a collaborative effort working with an alternative school, teachers at a public school, people who STEM, although that's everyone, and interdisciplinary researchers. So just to give you an overview of the larger project, it started out with a case study with an autistic middle schooler. And then we did, in the next iteration, we did a series of semi-structured interviews with neurodivergent and neurotypical kids. So one branch of work, which I'm kind of working on now, looks at balance-based ways to explore other math concepts. This line of work built towards applications in one in a museum study and one a classroom study. So what does it look like to be learning to the sense of balance in these settings? So we're going to focus here today in the kind of midstream, this iteration called balance graphing and the set of task-based interviews and kind of where did we get to from what we learned to do those task-based interviews. So for this project, I brought together collaborators and students from many different disciplinary backgrounds. I think that's one of the great things about design-based research. Everyone has something to offer. So engineering, computer science, data science, psychology. Okay, so I want to take you through the same kind of process that we started with in terms of the design problem that we started with. The design problem of Balanced Board Math is actually 2 design problems intersecting. So the first one comes out of especially research in occupational therapy, somewhat taken up in special ed. The problem is the sedentary classroom ignores students' need to move for sensory regulation. So it ignores the fact that research in those domains has found that basically we all have certain neurological thresholds to sensory input, and that means that to be in an optimal state where we're not overstimulated and we're not understimulated, we might need different kind of our optimal range might differ. That applies too to modalities that we don't tend to think about much, like the sense of balance. Some of us are perfectly fine sitting still a lot of the time, others aren't. From this perspective, Connor was somebody who needed more stimulation in order to be in that optimal state. So when he was on the balance board, he had more sensory stimulation that helped him be in a place to be able to engage affectively with his homework. Stimming, which we mentioned earlier, is a way that people can spontaneously seek to stay in that optimal state. We can provide ourselves the kind of stimulation that we need. But that's not very welcome in most classrooms. It's often targeted for extinction and applied behavioral analysis therapy for autistic kids. I was talking about this earlier with folks, like in an interview I did last week with a person with ADHD. They mentioned that they used to get detention for stimming all the time. So it's a common site of discipline for many learners. So current solutions to accommodate the range of sensory profiles involve sensory supports. So that's things like bouncy seating that enable people to meet their sensory needs, or sensory activities that happen outside of the classroom, like sensory therapies. But these solutions don't actually change the instruction itself. They don't make the instruction more sensory accessible. This kid is on a bouncy seat, still doing a worksheet. The actual content itself hasn't changed. So when we come from an embodied perspective, this opens up, have we actually made the learning experience accessible? Or, is it really just a vitamin that you can take sensory stimulation on the side? Or, is the whole sensory manifold, should that be part of the conceptual experience? Problem 2 comes more from the learning sciences and this work looking at the role of the body in cognition, which is that normative math instruction neglects the theorized sensory-motor foundations of cognition. This is interrelated with a problem called the symbol grounding problem. So the symbol grounding problem asks, sorry, I'm blocking you, Mark. Where do symbols and representations get their meaning? And one answer is, well, they get them from relating them to other symbols and representations, things like language or the number line. But then where did those things get their meaning? And so it's been proposed that when you kind of trace this back, ultimately, the meaning grounds in our sensory motor interactions with the world, right? Things like accumulating objects or moving through space is what kind of ultimately grounds all of those interconnected symbol systems in some meaning for humans. So typical instruction may or may not connect all the way to that level of experience. And from this perspective, Connor was getting lost in the numbers in the first place, such that he needed more sensory stimulation because the symbols were not well grounded for him. I want to make sure you have a spot.
Thanks.
There we go. Okay.
Keep going.
All right. There we go.
It's a good example. It's happening now. Oh my God.
There we go. Yes, it goes without saying, stimming is welcome in this talk. Existing solutions to this problem are a set of kind of explicitly movement-based. Seeing you like peering around me. Or a set of explicitly movement-based pedagogical approaches that are emerging in the learning sciences, where kids do things like walk on a physical number line or move their hands in order to ground the meaning of concepts in movement experiences. However, to date, these solutions don't pay attention to the sensory qualities, the sensory experiences that they offer. So a child might still be asked to sit still and just move their hands, or, it's very difficult to sit on a bouncy seat and manipulate a VR graph at the same time. So there might be conflict between meeting their sensory needs and participating in these kind of still potentially prescriptive bodily experiences. So how could we resolve these conflicts and make instruction itself accessible through adaptive sensory stimuli? How could we integrate movement for regulation and movement for learning into one experience? So that's kind of the core question driving this design. So the design conjecture is you can integrate them, that they can be integrated within the same sense of activity. So a great context to look at this integration is this bodily sense of balance. It's common in the stim of rocking, and It also, neuroscience research has found that this vestibular sense, our sense of balance, plays a strong role in both cognition and emotional regulation. Oh, since it's not in our Western top 5, a quick orientation, the vestibular sense, it's in our inner ear, and it involves both a sort of set of XYZ oriented semicircular canals that we can feel the kind of position of our head, and these little crystals attached to hairs that orient to gravity. And yeah, foundational research has found that it plays a critical role in cognitive development, in spatial memory, and even specific mathematical abilities like arithmetic. But also it's a strong driver of emotional regulation. So think, for example, of rocking a baby or jumping on a trampoline. Vestibular experiences are a powerful lever for impacting emotion. So not surprisingly, it's a common feature of many stims. Balance also plays a metaphorical role in mathematics already. It's been described as a seed of algebraic thinking, think balancing equations. And yet we don't really explore what it would look like to ground things in our bodily sense of experience. So we decided to focus on this sense for the project as a kind of natural nexus for integrating sensory regulation and cognition. So how do you go about designing for stimming? So at first I thought of this as, well, we just need to make it possible to crank up the vestibular stimulation available. But through some initial testing and more exploration, I realized that two things. One, that kind of stimming, it needs to adapt to the moment. You might not need the same intensity one moment that you do another. And it has this rhythmic, repetitive quality. So here's the kid stimming, as you can see, right? And that repetition, in terms of how that might impact your nervous system, is important because repetitive movement is more predictable. So I started exploring what it would take to kind of foster this kind of rhythmic activity. That's where the balance boards come in. So this is a kid using the balance graphing activity, and you can see that kind of sensorially, it has some strong similarities to this spontaneous stim. And throughout, I also wanted to make sure that kids could engage at variable intensities so that they could kind of self-adjust to their sensory regulation needs. And then how do we actually make this vestibular experience congruent with math concepts? How do we set it up as a resource for exploring a mathematical domain? So I decided to go with trigonometric functions because they are naturally periodic as a first context to be looking at this. Basically the mechanism is we put sensors on the side of a balance board. So this is kind of what it looks like inside. Usually they're affixed to the side of a very large balance board and use it as an input for dynamic graphing. So in this context, how far you rock corresponds to the amplitude of the graph you're generating. How quickly you rock controls the frequency. So you can kind of feel these different parameters that are actually the parameters of trigonometric functions that need to get differentiated when you study that at a later age. So here's what the kind of technical implementation looks like. So we use an inclinometer sensor that fixes the position of the board and relays it via an Arduino, and then we project a set of different programmed activities that augment your graphs in different ways to help you pay attention to things that are mathematically valued in math cultural practice. Important thing to know to make sense of the data, or what you'll see, is the mapping. So when you're graphing, X is time and Y, so you control Y. If you rock forward or kind of downhill, it will go to the negative numbers. If you rock uphill, it will go to the positive numbers. That's the mapping. I'll give you a couple of examples of the kinds of activities that the kids explore here. So the first one, so they're discovery-based activities. So we tell kids things like, in the first one you'll see, we tell them, try to find the green stars. And then they explore what kind of rocking can give rise to that. So he's exploring this activity for the first time. He's in kindergarten, I believe. Okay, so he just found a green star, and now he's finding them on both sides. posit so I can. So he was finding those green stars on both sides of the x-axis, right? Because amplitude is a symmetrical quality. And you heard there's also sonification that goes with the different factors. Okay, and then this one is about frequency. The directive they get is try to make the whole screen turn green. And how it works is that each kind of need context before you see it. Each period, each cycle of rocking, the background will change color depending on the period length. That is what frequency they're rocking at. And so the different frequencies give different color feedback. So they have to figure out how to rock at a consistent frequency to make it consistently green. And you can hear the sonification that kind of highlights the local minimum, local maximum, and passing through the x-axis. Those are green. It's a little distorted color. But so as he naturally varied his frequency, he got different colors, and then through exploring multiple rounds, the kids generate hypotheses about what gets green stars, what makes it turn green, and they kind of start to attune to features of the graphs in a different way progressively and test their ideas. Given the conceptual focus on graphing, another relevant conjecture from embodiment theory, specifically in activism, is that education serves to enculturate kids into understanding static images as offering opportunities for action. So from this theoretical perspective, we can understand the meaning of a graph because we can see it as having certain action affordances that help us connect it to that grounding in our sensory motor experience. So the second design conjecture of the project was that generating graphs through these kinds of vestibular activity will bring kids to see graphs as affording movement. So imbue them with action affordances, essentially. So the research questions flow from each of those conjectures. Basically, first question is, can the same movements actually serve sensory regulation and cognition in an integrated way? And then the other one is, can grounding in these kinds of vestibular activity change how kids perceive graphs? Can they come to perceive new action opportunities in a static graph? So to address these questions, we conducted semi-structured interviews with 21 elementary and middle schoolers. So there were neurodivergent and neurotypical kids. We tried to capture a broad range of sensory profiles in the sample because we used an occupational therapy sensory questionnaire to monitor that. Because we were interested in how kids are adapting the vestibular intensity to their sensory profile. And we wanted to make sure that, if there are differences in stimming for autistic or ADHD kids, that they're represented as well. The interviews took place at our lab, at an after-school center, at the alternative school, and kids participated individually or with a peer. And the way it was set up is that we would tell them the task, we would invite them to try the graphing, and then in between rounds, we would ask them questions like, did that work how you expected? What do you want to try next? And they could try each of the activities as many times as they wanted or choose to move on to the next one. Most kids played for about 30 minutes with the activities. To address the second research question, we also, before and after they interacted with the balanced graphing, we showed them pictures of graphs and we asked them to describe them and to show them with their body. There's previous work in math education that shows that people who are more expert with graphs, they tend to gesture in a different way. So when you're less expert, you're more likely to gesture in a way as if you're seeing the graph. So like you're tracing it on a piece of paper. And those with more expertise are more likely to gesture as if being the graph. So using more of their body, sometimes positioning themselves as if they're like inside of the graph, riding the graph, as opposed to looking at it as an object. So we wanted to know, could this kind of activity cultivate being the graph? So we used the criteria from that previous research to code the videos and check that quantitatively. So I'll share the results across both of these together. So first off, looking at sensory regulation, we found that children rocked a lot, even when the task didn't require it. Children of all sensory profiles rocked, but those who were more sensory seeking, whose questionnaire suggested that they prefer more vestibular stimulation. They rocked more frequently, and you might be able to see they rocked a lot more intensely. Kids like this are the reason why we installed bumpers on the sides of the buildings. Actually, we replaced those with stronger ones. This is an example of a kid who rocked in a very, very limited way, and she actually even would take breaks and get off the board in between, so very low vestibular seeking child. So we did see this kind of self-differentiation of sensory intensity by the kids. Learners also were generating graphs with their rocking. And as they did this, they started to progressively connect features of their movement with features of the graph. So here's an example of a graph that this child has just made. He's exploring an early frequency activity. And he says, I went a lot slower that time, and I only have like 3 hills, like cycles. So he's connecting his rocking frequency on the board to the number of periods that fit in a given unit of time. So this kind of connection tends to be a sticking point for learning about trigonometric functions, and the kids are using these experiences of rocking to make sense of and reflect on the features of the graphs. What about the kids' gestures? So I will show you one example. This is a first grader. Before she interacts with the board, you can see she's doing this kind of one finger tracing, and actually that's larger scale than a lot of the pre-gestures that we saw. And this is her in the post. So you can see she's actually lifting her feet off of the ground, and very clear vestibular involvement. Not every case was like this, but we did see that, looking across participants, there was statistically significant increase in being the graph. We looked specifically at how much the vestibular sense was involved in these gestures, and we did see an increase across kids. In our analysis of the rocking that arose, so we saw that it was serving sensory regulation in cognition, but we also saw it doing something else. We discovered that kids were using rocking to communicate about features of graphs. So as an example, these two were kids at the alternative school. One is autistic, one is non-autistic. So this is a non-autistic kid and this is an autistic kid. And this kid said, I'm going to make more green stars by doing this. He rocked very quickly, but with a low amplitude. And this kid said, well, if you do that, then you're going to get little lines. So he's showing the amplitude that would result from a rapid but low amplitude movement. And then he elaborates like this, and he demonstrates a high amplitude movement on the board. So he was able to recognize the way that his peer was perceiving the graph through his peer's rocking movement, see that his peer was not attending to amplitude, but only to frequency, and to use rocking as a way to draw his peer's attention to that quality. So to recap, we found that kids did indeed stim, this supported stimming, and the kids self-differentiated the intensity, which isn't something people have ever really looked at in an educational setting before. So this suggests that if we build activities and to be sensory adaptive, kids will differentiate the intensity for themselves. We found that children's gestural expressions of graphs became more dynamic and large scale, suggesting that by connecting these bodily experiences with the representation led them to potentially perceive action affordances that they didn't see before. I want to just add a note that the point of this design is not a balance board for every child. It is it's just a proof of concept for the vestibular sense as a resource more broadly. And there's many low-cost ways, low-tech ways to engage the vestibular sense as well, things like walking and rotation. Just want to gesture towards that.
It does beg the question that rocking chairs in classrooms is not a good thing to have.
Maybe,
Just
right?
generally speaking.
And I think that it also invites the question of how do we engage with tools like rocking chairs in the classroom, and how do we think about making those part of the ways that kids actually explore. And we found that children's rocking movements, they function for sensory regulation and cognition, and they became communicative. So this suggests that stimming and thinking are not inherently separate processes. We even saw instances where kids were stimming in the background, and then someone would talk about an idea, and then they would modulate their rocking according to that idea that their friend had raised. So it seemed like there was this very fluid relationship amongst the different functions of stimming in the data. To kind of express what we learned in terms of some design principles that could be explored in other contexts, it seems like to make learning stimmier, we want to equip STIM. So we want to kind of invite the kinds of bodily engagements that meet sensory regulation needs, position those stems as epistemic actions, as resources, as congruent with the things we want kids to explore. And we want to, through that process, legitimize these forms of movement as part of disciplinary discourse. So I'll wrap up talking about balance board math by showing you how we iterated based off of this. So we were really interested in this interactional stimming that came up. And we wanted to foster more of this kind of multimodal dialogue amongst the students. So at this point, we teamed up with high school teachers because we thought the classroom is a great context to be looking at discourse. We wanted to specifically design an activity that required the kids to coordinate their movements with each other in order to require more dialogue. So the result is an activity called function addition. So in function addition, there's two boards. In the classroom, they kind of were in small groups, and each group had a challenge, and they would rotate testing ideas on the board. And then the rest of the class would give input. So in function addition, one board draws in blue and one in orange with the same mapping as before, but you can also see the real-time sum of your two graphs. And the challenges involve trying to create different kinds of sum functions. So in this example here, the kids had the challenge of trying to make a really high amplitude sinusoid. And the only way to achieve that is actually for them to reach the maximum amplitude of each of their boards together at the same time. So they have to coordinate their phase relations to achieve that. Another one of the challenges is to try to sum to a line that traces the x-axis. So there are very easy ways to do this, like don't move at all. But the kids came up with many, many different solutions, and actually all the groups that we worked with also came up with solutions like one I want to show you right here, which is very technically, like movement-wise challenging solution of generating anti-phase sinusoids that perfectly cancel each other out. There are a few, you can kind of, you can look here to see where the graph is happening. These are different views of the same group. So you can see that they're trying to perfectly coordinate. You can look at what their movements are looking like. There you go. As they were working on solutions like this, they came up with many strategies to try to refine their coordination. They did things like clapping or counting to try to align their frequency. They used coordinates to reference, okay, rock to 2, so that they could get their amplitudes more perfect. They sometimes brought in their peers to help facilitate, like tell us which way to go, so that they could refine their amplitude, frequency, and phase synchrony to achieve the most perfect straight line. In this classroom study, we looked at whether kids did better on kind of a traditional pencil and paper function addition test, and indeed they did from playing around with these activities. And this is anecdotal, but when I tested those materials with a group of researchers, they also improved on their function addition. I think that the kind of low floor, high ceiling nature of these activities mean that they're, they were generating all kinds of really complicated sum functions in their explorations. And in the museum study, we had little children, and they were exploring things like anti-phase rocking. Let me move to my next slide. So we've seen a snapshot of a study that reimagines one norm of bodily movement in the classroom. The next project, which I'll share more briefly and is kind of in an earlier stage, is TeleTangibles. And this one focuses on the norm of heavily using visual representations in the classroom. So this project centers the embodied resources of blind and low vision students, specifically their expertise in using bimanual exploration to understand spatial information. So the tactile and haptic practices that this population has expertise in. So the focal underexplored modality here is the haptic modality. And this project intentionally spans multiple STEM domains, but we'll talk about two examples, one from geometry and one from magnetism. And it involved and continues to involve co-design with blind and low vision youth, sighted youth, teachers, and researchers in different disciplines, including haptics researchers, folks from interactive simulations in the physics department here, and a couple of us learning scientists who are focused on the interaction design and how it yields different kinds of learning and conceptualizations. So a design problem for this project is that visual representations are inaccessible to blind and low vision learners, and that this limits their opportunities to explore spatial concepts. Currently, the way that this gets solved typically is that they get access to verbal descriptions of visual representations or tactile translations of them. But embodiment perspectives highlight that this might not actually be an equitable equivalent to take a visual thing and translate it into another modality might not actually invite the kinds of interaction, perception, action experiences that can give rise to the same kinds of spatial concepts. So we wanted to explore what a haptics first approach to learning is. We started with a core spatial concept, which is shape concepts in geometry. So a common issue with shapes is that kids only recognize the categories if they're in their canonical textbook orientation. Like, that's not a square because it's not squared to the bottom of the page. And so we wanted to kind of see how dynamic haptics first conceptions could change this. So the earliest version of quadrilateral looked like this, made of chopsticks. But you can kind of manipulate different and look at how different shapes relate to each other. So that's the early version. Later versions started to involve 3D printing and being able to extend sides. And we wanted to connect those haptic interactions with math language. So to use the tangibles to also ground the math category words. So this is a computer vision version where it pairs with this simulation built by the SPET folks for this purpose. So this simulation allows voicing of the shape categories. When you make a square, it says square. When you and it can also voice the properties of the different angles and side lengths. So what kinds of conceptual interactions does this enable? This is an example from a blind middle schooler at a Braille school in Chile. And so he's interacting with this tool. He has a rectangle. Here we go. He has a rectangle. And what he's doing here is he's pushing these lower corners together to make a trapezoid. And then the system says trapezoid. And he feels along the sides, these two sides, and says, now these sides are not parallel. Mm-hmm. So he's coordinating he's seeing a trapezoid as a transformed rectangle because he's connecting between the different shapes. And he's connecting between the different shapes and what changes about their properties. At another point, he had a rectangle and he was asked whether any sides were parallel. And the first thing he does when he's asked this is he touches these opposing corners to feel the angles. And then, so he touches to kind of to know, and then he says, these are parallel, indicating those pair of sides, and so are these. So here he's using touch to show. So he uses a different form of touch to be able to coordinate his perception with his interlocutor. This moment of grabbing the two corners is especially cool in light of previous work I've done in looking at eye tracking. So I've found that I found quantitative evidence that when kids are doing these kinds of embodied design tasks, they start to look in new ways, just as they're about to kind of have a conceptual breakthrough and start to talk in a different way about the math concept. So here's an example where a kid is exploring a ratio activity, and they're looking at just at kind of where their hands are on the bars. And this, whoops, I thought I was trying to just show you this. They start looking at this new point, the projection of one bar onto the other, as they're about to start talking about in a more ratio type way, a more multiplicative type way about the two quantities. So these kind of new ways of perceiving that organize different aspects of the scene and coordinate them together are called attentional anchors. And to date, they've been looked at as visual entities in looking at embodied learning. But when we see this kind of action that integrates the sensing of the angles of multiple sides of the shape at the same time by grabbing these two hands, we see an instance where this kid is engaging in a haptic attentional anchor that helps him be able to perceive multiple and coordinate multiple properties of the shape at the same time. So this questions the kind of oculocentrism of research on perception in research in the learning sciences and more broadly. So just to give you a teaser of where we're going with this, we from that point, from the quad, we wrote an NSF Riedel grant, which was we're in year 2, and where we're building reconfigurable haptic modules that can be used with different STEM contexts, and doing some co-design work with blind and low vision youth to explore what that's useful for in terms of their learning. We shout out to Paper Playgrounds, some folks here were involved in developing. We've been using that to prototype with computer vision. I'll just give you one example of the kinds of things we're playing around with. So this activity is for feeling magnetic field vectors. So with one hand, you are holding a magnet, so you can move the magnet around, or you could adjust its intensity. And with the other hand, you have another one of our modules. So this is just it's just a round thing you can hold, basically. This one, it's sort of like a joystick, and it can convey direction and intensity on your palm. So you can feel basically a vector in a tactile sensation on your palm. So if you move one hand over the field, you can feel the changes in the field vector. So through that, we're hoping that we can foster kids to be able to kind of construct for themselves the attentional anchor of this shape of the magnetic field. So by moving dynamically over the field and feeling how the vectors respond, they can discover what the shape of the magnetic field is. Okay, so we've seen these two cases where the embodied resources of marginalized populations have expanded our understanding and implementation of embodied learning. From here, I want to open on to where I see this going. And I'll just suspect to be. Okay, so social psychologist Kurt Lewin once said, "There's nothing more practical than a good theory." Embodiment theory, it invites new ways of conceptualizing what equity in instruction looks like, and it invites new ways of conceptualizing, kind of making sense of the possibilities of new technologies. So I see this as kind of the core of the work that I'm doing. Central to this work is the need to deepen engagement with marginalized learners through participatory and co-design methods. So that's really the creative engine for this work. So like a next generation beyond balanced board math is I plan to explore a broader range of STEMs through participatory co-design with neurodivergent kids. Another important direction is looking at coordination activities and interactions of kids who have different sensory profiles from each other, blind and sighted learners together, and how multimodal experiences can facilitate shared learning. There's much more to unpack in terms of underexplored modalities, the cognitive and affective impact, from proprioception to tactility to vestibular sense. I had a synesthete tell me that they could smell the answers to math problems as a child recently. There's that. We need to look across concepts in order to really be able to test the limits of what embodiment theory, how embodiment theory pertains and what grip it can get on the nature of conceptual understanding. For theoretical depth and empirical rigor in studying embodied learning, we also need robust tools. So another line of my research focuses on analytics that can capture complex learning trajectories. So multimodal learning analytics, nonlinear methods that can help us see phase transitions as kids kind of change from one way of making sense to another. And I've used electrodermal activity and eye tracking and movement tracking to look at this. So I plan to kind of weave that in more deeply with design projects. And then partnering for sustainable impact is really critical to this work. Partnering with educators, interdisciplinary scholars, in order to expand, like maintain accountability to impact and getting things out to people that are developed. It's an interesting time. That's all I'll say about that. So to conclude, we've seen several ways that we can remediate entry into conceptual learning to resolve contradictions between sensory and motor ways of exploring the world and the way that we invite kids to explore concepts. Emerging technology is changing our interactions, and with it, this will change cognition. So to understand the role that the body has to play in that will be really important in making sure that we don't replicate or exacerbate inequities in the way that school gets done. And through this work, we found that diverse ways of sensing and moving can inform theory and design, and that neglected sensory modalities, they serve as ways to enable kids to intuitively and kind of collaboratively explore abstract ideas. So I plan to partner with youth and educators and interdisciplinary researchers to develop these insights into both useful theory and useful tools that can make education more inclusive and effective for all students. Thank you. It's something one of the students in the classroom wrote. So we asked for their feedback on the activities, and he wrote, "It was cool, better than just sitting there. School would be better like this." And
This is fascinating, and I think the way you conveyed the meaning or the impact behind all of the work based on the examples. You might not have a question yet because you talked about this in future work. You might not have an answer for that yet, but like I was curious, in the example for stimming, you started with the case of that student who was able to do a lot more problems just by standing on a balance board. And in that case, I'm not sure what the problems were. They may or may not have been related to the activity on the balance board. And through the work with the balance board, with the sensors, you've been able to demonstrate that there's that inherent connection between your movement and the concept you're learning. Do you have insight or thoughts about what it would be like when the concept may not be directly connected to your movement on the balance board? And
I would say that's the norm in instruction right now, right? But I think that stimming it often plays a sort of rhythmically organizing role, or it kind of helps to galvanize resources to help maintain focus on a central task. So even if you don't get the explicit congruence that you could design for, that would make that role explicit, it's already present in for many forms that stimming shows up in, but because it's kind of under the radar of people's consciousness, they may or may not even speak about it. Neurodivergent people tend to be able to speak about it more explicitly because they've had to pay more attention to this aspect of their experience since there's more misfitting.
I have a related question, so I just want to build on that.
Yeah.
So I hope you were done.
Yes.
Okay. It was I was wondering about this aspect of the sensory regulation, where part of it, what are the forms of evidence that you're building on now and analytically for it? And what are things that you can imagine doing more analysis around in the future that maybe you have not included?
Yeah.
Because what I saw you including was, person A, person B have different sort of stimming tendencies, getting to their preference.
Yeah.
So there's that one. But
Fitting,
are there ways that they talk about it, ways that they move, ways that you can see their faces or limbs related to this?
Yeah.
Are you using that in the analysis yet, or do you in the future?
Great question. In that data set, we were looking also in a lot of detail qualitatively at all the forms of stimming that appeared. So rocking was one type, but other types of stimming also appeared. And we looked at every instance of stimming, and we looked at each instance in terms of whether it had any congruence with the ideas that were being talked about. So there were instances of stimming that we could say explicitly, wow, he's rocking the exact number of periods on that graph. That looks like he's just stimming in the background, but like it's directly related. Or like he's rocking and then someone says something about the big hills, and then suddenly he rocks slowly to generate big hills. So instances where the congruence was explicit, but not always. Another way that I've explored, looking at the kind of affective dimension of it, is with electrodermal activity. So in a little ISLS conference paper, we looked at the differentiating whether movement that was for the task versus movement that was stimming, whether they had different impacts on electrodermal activity for kids. It was just a comparative case study of like a high sensory seeking student and low. And we saw that they actually had different impacts. Like for one kid, stimming was more calming, and for another more alerting. So it seems like there's this complex picture of how kids are using stimming. And I think that both quantitative and qualitative methods will be necessary to really tease out the complex way that kind of sensory, affective, cognitive activity are playing out together.
Did you look at heart rate variability here too?
Not yet, but I would like to. Yes. Absolutely.
Exactly.
Yes, I agree. Yes, I think that will be a really helpful metric to use. Because we were using empathic at E4s, which also you could get heart rate variability from there, but we just haven't explored it yet. Yeah.
I'm thinking about so the learning works. You can see that the learning works, and so just on its own. But from the perspective of ableism, thinking about how we recognize its all the different pieces of that that contribute and talk about together. I imagine a co-design talking about this stuff. Yes. Have you thought about what happens after co-design within professional learning with teachers? So when we're using these as an opportunity to go against this norm of the way classrooms are set up, how do we talk about that with kids or with teachers?
It's a really important question. And like, I do conceptualize building these kinds of tools and working with educators on them as a way to try to shift some systemic ableism coming in through the tools. But in terms of how to talk about them, I mean, I think that a challenge for teachers is like that the a lot of the structure around them, bake in certain forms of assessment, certain constraints on their time. And so there can be this tension between maybe buying into the ethos of a project, but what, you know, the tension between Monday and someday, right? That they have to deal with. And that's why I like to engage teachers from early on in this work, because I think it'd be like, if we just co-design really great neuroaffirming tools, and they stay limited to just the kids that were a part of that, then that seems like it's not helping to engage in systemic shifts. I don't think that tools alone can do it, but that's where I fit into the ecosystem. And I can tell you,
Kind of like rapid
and
the teachers can say words while they're
yes,
actually really
yes, and experiencing these kinds of embodied interactions have an affective experience on the teachers. Like, I was running a workshop with a group of educators from China where there's really strict, at least where they come from, like really strict, not even a water bottle on your desk. And when I started talking about stimming, there was audible gasps. Someone was translating for me, and like the room like exploded and people were talking. And she said like, that is very controversial. But when they got on the balance boards and they got to explore this kinds of activity, they started asking questions like, where can I get one for the school? So I think, you know, the power of embodied experience also apply, you know, teachers also, their cognition and their affect are imbricated together. Like having a new kind of learning experience can open up new possibilities for how teachers imagine what teaching would be. Yeah.
I think I have on the slide from embodied learning has been already there for
yeah, since the 90s. Yeah, well, the theory. Yes, right. Right.
And then, I mean, these guys, you know, like example, not really like that.
Yeah.
So I'm just on it.
In terms of how it can make it to the classroom. I mean, I think one learning sciences response to that is the genre of design-based research, the community engaged approach that seeks to build with in order to figure out how to actually do it in a real learning ecology. Because, you know, there's teacher training, there's like how schools are set up, there's standardized assessments that all shape the constraints that schools are learning under, and there's not always good first of all, connection between where they would even hear about these ideas, dissemination, but then also to make sure that they could actually be implemented in the kinds of context that they're operating within. So there's, yeah, I think that educators have to be a part of what it will take, and schools of education.
That would be a good target.
Yeah, absolutely. Waldorf has a lot of, and in general, early childhood has more tendency towards embodied engagement and recognition of the importance. Things like Waldorf Montessori or
yeah, but that's a long enough, big enough sample size to prove it out in a community that would culturally take it on. You know what I mean? Can try it. So. Public education system. You know?
Yeah.
I mean, how do you translate things effectively? Otherwise, it's kind of, does it matter?
Yeah.
You know what I mean?
Well, I mean, I'm optimistic about, you know, having worked with a high school that it's not completely incompatible with the constraints that teachers have.
Yeah, I'm saying how do you get some level of scale
out
at a level of scale?
Right. Well, museums is also a great site for this. We were talking about this yesterday. Museums get so many people in. So like one of the contexts, I think I have a picture right here we go. This is an installation at the Copernicus Science Museum in Poland. And I've been working with them with this with a big group of all different collaborators, finding a Zoom time is really fun. So basically this is about, Cartesian coordinates. So one person controls X and one person controls Y, and you're navigating balls through a maze and progressing through different ways of, eventually you're using coordinates to do that. So this installation, working with this museum, gets hundreds of thousands of visitors all the time, and we can even like iterate the design in context and say, we think that this facilitates the work with coordinates, but what if we change the order? Do people do better or worse? So in terms of getting like high power data sets to be able to answer questions, informal learning spaces can be really powerful and messy context for that.
So, I mean, empathy bonding methodologies we are like not adopted yet.
Yeah.
Are there any past examples that's successful to adopt it from that?
Incorporated in learning settings. I mean, there's lots of projects that have been taken up in different settings. Like one example that comes to mind is that had more reach is a project called Graspable Math, where they were teaching algebra, and they were focused on kind of the way that we treat algebraic terms as objects, and they set it up so that you can kind of actually manipulate the terms the way that that kind of foster that way of seeing them. And since it's like a tablet app, then it had more uptake. Why did it become popular? I mean, I think it has a lot to do with networks, and then also tech. Like one reason why working with FET is so cool is like they have hundreds of millions of users per year. So you know, the digital quadrilateral that we built is just open source and getting used by teachers all over the world. And making the materials available open source, like people take it up in unexpected ways. That's how we ended up, you know, someone else built a quad based off of that open source stuff, and that's why I had that data from Chile. Like, yeah, so they can like just, you know, make it. And so I think it's both about the nature of designing tools in a way that can be accessible and taken up. I mean, like working with Arduino is not going to be available to every teacher. And I am excited about how like expertise that people have here can guide thinking about like what kinds of ways of building these tools can enable them to be more accessible to more teachers. But then connecting with teacher training, like shifting the kind of connecting that embodiment perspective into how people conceptualize what teaching is. Well, also
my question, and then you don't have to answer it. It's not just so why does it say for the informal conversation and the other side?
Yes, and you can play with stuff if you want.
So the thought I had was chose very cleverly to pick for being the graph and the balance board. But that seems like a black art. It's like, how do you match the thing that you're trying to get people to think about or learn with the particular form of physical?
Yeah.
And maybe that's the method that Rio was talking about. Like how do you connect these two things?
That is why I ended up replicating across a number of different math concepts to be able to show like, no, it's really not just periodic functions. Like sense of balance has this really, you know, so balancing like equations and inequalities is one context that I'm working with kids with right now, which are analog activities, just using blocks, and like negative numbers and absolute value and the additive inverse principle.
It seems really rich.
Yeah.
The question is, how do you, if you're a teacher wanting to design an activity that right, how do you match these things? I have no doubt that this has a global implication. Or for example, you chose graphs for trigonometry, but it could have also been moving around with a circle.
Yes,
And
actually, there is a unit circle activity. Where they kind of reinvent sine and cosine, like sort of like an Etch-a-Sketch type action.
Sophia, you reminded me of last week on spring break, my two teenage sons tried to teach me how to play Grand Theft Auto. People don't know anything about it. So I was doing this and they were doing like that, and I'm using my embodied knowledge. And then the little joystick. I was like,
let's see. But,
Trying to match my embodied knowledge of that to.
and learn,
Yeah, I thought it was hysterical.
because there is the, you know, when this is, if this is a proximal tool for this
Right.
distal effect, you have to come to kind of, there's the coupling between you and this thing, and then between this thing and that thing that you have to progressively tune before you can kind of just focus on the distal thing, and this is,
Exactly.
goes out of your awareness. Yeah,
I'm gonna open the doors of people going through something. Continue the conversation.
yes. But,
Thank you.
yeah, thank you.